Let's start with observability across hops. We know there are 5 stops on this journey. How do we instrument them to track a single request all the way through?
This requires comprehensive distributed tracing. You have to inject and propagate a unique identifier like an X request ID header, starting at the very beginning at layer 1, your ingress controller.
And that ID has to be passed along at every step.
It has to be passed through the application logic at layer 5, and ideally it should be logged by the CNI plane at layer 4 if it supports it, which is something you see more in service mesh environments.
Because if the request fails 5 layers deep, we need that one ID to link the ingress access log, the application trace, and any intermediate proxy logs all together into a single story.
And your metrics have to follow this same path. Instead of just measuring end-to-end latency, you should instrument your system to capture latency histograms across each hop.
So measure the ingress processing time separately from the application processing time.
Exactly. Measure layer 1 time, layer 3 translation time, and layer 5 application time. If your total latency suddenly spikes from 100 milliseconds to 500 milliseconds, your hop metrics will immediately pinpoint whether the application added 400 meters of delay, or if the kernel forwarding at layer 3 or the network fabric at layer 4 suddenly became the bottleneck.
We talked about packet captures earlier. Let's structure that knowledge based on the layers we've defined.
Right. For debugging layer 4, the CNI, remember the key difference. If you run TCP dump on the node's physical interface, you are observing the physical road. If you're using an overlay network, you will see VXLAN headers.
And seeing them is a good thing.
Seeing them confirms layer 4 is doing its job of encapsulation. Then you run TCP dump inside the pod's network namespace. This is observing layer 5's input. You must see the clean original packet here. A mismatch between these two capture points immediately isolates the CNI's VTX key or routing function as the problem.
Next, let's summarize security based on our 5 layers. It's not just one thing.
No, it's defense in depth. Security is layered. At layer 1, we establish you have TLS termination and potentially a way-for rate limiting at your ingress. The first level of internal segmentation happens at layer 2 with RBAC, role-based access control, which controls who can define and modify services and endpoints.
That's control plane security, preventing someone from accidentally or maliciously rerouting traffic.
Right. But the real data plane security, the packet level security, starts at layer 4.
With network policies.
Yes, layer 4 is where network policies live, providing the microsegmentation that restricts pod-to-pod communication. This is what prevents lateral movement in case one of your applications is breached. It acts as a firewall inside your cluster fabric.
And you can take it even further with a service mesh.
You can. If you use a service mesh, you introduce another powerful layer of security at layer 5 using mutual TLS, MTLS, via sidecar proxies. This encrypts traffic even between pods running on the very same node, ensuring a strong layer 7 identity validation that's completely independent of the underlying CNI.
Finally, let's consolidate our understanding of performance trade-offs. This is the ultimate consequence of choosing specific implementations at layers 3 and 4.
The performance battleground is really between the rule writer at layer 3 and the fabric at layer 4. In layer 3, the choice between itables and IPVS defines your rule lookup efficiency. As we noted, the cost of that sequential traversal in itables grows linearly with your service count, while IPVS uses constant time hashing lookups, offering significant CPU relief at scale.
And in layer 4, it's all about the encapsulation tax.
The overlay cost versus the routed speed. Overlay networks like VXLAN add header overhead and potential MTU issues, but they are simpler to deploy on almost any underlying network. Routed networks using BGP offer cleaner, faster tackets, but they introduce the control plane complexity of managing routing protocols. The choice is always complexity versus throughput.
This leads perfectly into this deeper analysis of the 2 dominant approaches to advanced networking today: the service mesh sidecar versus the eBPF data plane.
This is where modern Kubernetes networking mastery really emerges. In the traditional service mesh sidecar model, an Envoy proxy container sits inside every single pod right next to your application.
And all traffic, both ingress and egress, has to pass through this sidecar at layer 5.
All of it. The benefit, of course, is that the sidecar provides incredibly rich layer 7 control, policy enforcement, MTLS, observability.
But you pay for it.
You pay the latency penalty. Every single request now involves an extra hop into the sidecar proxy, an extra context switch between kernel and user space, and an extra process running, which substantially increases CPU consumption and reduces throughput. Benchmarks often show a 5 to 10 millisecond latency increase per hop, which is completely unacceptable for ultra-low latency applications.
But the alternative, using eBPF-based CNIs like Cilium, It fundamentally changes the architecture.
eBPF cuts that sidecar out of the hot data path entirely. Instead of routing traffic through a separate user space proxy, eBPF programs handle Layer 4 and even a lot of Layer 7 policy enforcement directly within the kernel space attached to the network interfaces.
So the performance is drastically higher because we're eliminating the context switching and the extra hop latency.
You collapse Layer 3, Layer 4, and much of the Layer 5 security and policy layer into one highly optimized in-kernel fast path. The downside, however, is that while eBPF is incredibly powerful, it is kernel dependent. You lose some of the flexibility and language-agnostic visibility that a user space sidecar can provide.
So it's a trade-off. Unparalleled speed and efficiency versus the flexibility and mature L7 features of a dedicated service mesh proxy.
For ultra-high performance clusters, eBPF is becoming the inevitable path.
This synthesis really shows that the 5 layers are not isolated. The choice you make at Layer 4 fundamentally impacts the performance ceiling and the security model you can implement at Layer 5.
It turns the maze into a map,